We talked about, especially in the second lecture, about outlier detections using linear regression. And we talked about the z-score. So how is the z-score going to be implemented and applied to iterative closest point registration? We perform the exact same steps that we've performed for our linear regression, but this time we're just going to do it for our rigid body transformation, right? So we start with performing our rigid body transformation. Why? So that we can get our basically linear regression there, which is in this case rigid body transformation. And then using that, we basically go and calculate the residuals. From calculating the residuals, what we need to get is the mean of the inliers as well as the standard deviations of the inliers. And then what we do is we regularize our data by means of our residuals. That's really what we do here as well. So once we perform that, we get the residuals. Why? Once we basically perform that, we basically get from the previous state to the final state how much difference every point has after that rigid body transformation, okay? Once we get that residuals, what we need is the estimation of the mean of that, okay? And what we mean by mean is that if we have a normal distribution, essentially a perfect set of data that only has random measurement errors, okay, our mean is our average. But if we have a situation where our data, so this is our normal distribution, for instance, okay? If all of the points that we have by means of the residual, okay, and normally when we have no systematic errors, this is actually going to be our zero. So the mean is going to be zero, okay, from the residuals. If we have perfect data around the mean, we basically are going to have all of our residuals essentially forming a normal distribution once we're putting it side by side, okay? In this situation, the mean or the mode of that is going to give us zero, and that is going to give us that mu. But in reality, we are not going to have that. Why? Because our data is going to have some outliers, right? As soon as we have a point over here, once we start mean averaging, this mean changes to somewhere around here, right? This by itself creates a problem. Because if we're now taking this data point over here, this is going to shift this much, okay? So we need to estimate this mu in a way that is robust to these types of outlying observations. This is what we call the breakdown point. We talked about this in the second lecture, if you guys remember. So now, essentially, we have to have an estimate of that, and we have to have an estimate of our standard deviation. Essentially, with all of these outlying observations, if we can estimate this mu here and the standard deviations of the underlying distribution, now we can regularize it and say, okay, any data point that is between 2.5 times or 3 times or whatever, plus or minus from that mean, is going to be our inliers. That is what the z-score provides. So the next part is basically we have to regularize it. Once we regularize it, then we have to say that the absolute value of this regularization of the data has to be less than or equal to a particular number. Where does that number come from? Which is this k that we're going to be talking about here. Where does this number come from? Does anyone remember? We said it ourselves, but there's a logic behind it. And it is the property of normal distributions itself, okay? Do you remember what the properties of normal distributions are? One is that the mean, median, and the mode is basically the same. The other one is basically if you have one standard deviation plus or minus from that mean, how many data points does that contain? 68%, but close enough. So this basically, so this is the property of normal distributions, okay? Plus or minus one standard deviation is giving us 68% of the data, okay? It makes sense, right? Because the majority of it actually starts basically going towards the mean, right? And it has to be more than 50% because actually 50% of the observations is basically there, right? What about plus or minus 2 standard deviations? how many points is that going to be? So if this is 1 sigma, this is going to be essentially another sigma here as well. 2 sigma plus or minus, how many data points is this going to contain? Well, a bit, less, but a lot of the data, right? How much is that? That's approximately 95%, okay? So this is 95% confidence. It depends on how much confidence we want to have on that regularized data for our outlier detection. Sometimes you need even more. So there's another property that is plus or minus 3 times the standard deviation. How many data points is that going to be? Any guesses? Very close to 100%, about 99%, okay? So these are all, like calculated and observed. So sometimes you want to have even more confidence, so you put this value of k as free. So this really depends on your data, amount of outliers that you have, and various different aspects, and how fast you want to remove some of these outliers as well, okay? So this is going to be plus or minus, this is going to be 99%. So there is some logic behind why we're doing it in this way. If you want 97.5%, that means 2.5. It's about 2.5 times. So k equal 2.5 times. Does that make sense? Yes? Okay, so how can we use this in our ICP? Basically, we've used it for our linear regression, right? So now we're just going to be using it for our ICP. There are a few ways that we can do this, right? And I'm going to be talking about various ways. If you take a look at the pre-lecture activity, I basically go through the code that is necessary for each and every one of these as well. But today I'm just going to be sharing with you the parts that are necessary, or at least the data points and the results that you're going to be getting if you utilize different modes of this, and what are the advantages and disadvantages of each. Okay, so we're going to start with what are these basically outlier detection methods. So the first way is our strategies, right? We talked about 4 strategies, if you guys remember. Do you guys remember that? Yeah? 4 strategies. One is if you use, let's say, univariate MCD, okay, you can get using that an exact method if you have only one-dimensional data for you to be able to get your mean and standard deviation, right? So that's the univariate MCD, and we can actually get an exact method using this. It's a bit more computationally intensive, but you can get that. Another way, this is strategy 1. Strategy 2, but before I forget, this requires exact outlier ratio. Doesn't mean that we cannot trial and error, but we need to provide that in advance if we want to use the exact algorithm. We can have an approximate there, but it's not going to give us the perfect deterministic result that we expect from that. So we can trial and error. Just to give you guys some ideas, it is possible to still estimate that by going back and forth between it, but we require a good estimate of that. The second one is to use the heuristic, which MATLAB already has. This is an algorithm called fast MCD. It basically, what MCD stands for is minimum covariance determinant. Essentially, it is proven that it can provide the least out or most outlier-free set of observations. Whatever basically set of observation between all of the sets of observations that provides you with the minimum of the determinant of the covariance matrix of those observations. Okay? This is what MCD provides. Make sense? Yeah? So there's 2 ways that we can approach this. One is to exactly calculate it. So there's an algorithm to do that. For one-dimensional data, which is our residuals that we're doing in the z-score, we can actually apply that. If you have multi-dimensional data, you cannot apply that directly. You can apply that to the residuals, but not directly to the data itself. The second is that heuristic, which uses a fast MCD, which uses a Monte Carlo-based method to draw different samples and then calculate the MCD and then perform what we call the concentration step, which we're going to be talking about a bit later as well, to really get through the data and see what the amount of outliers is going to be iteratively. So we're performing, let's say, something like the z-score iteratively, and every time you're basically getting more and more and more of this amount of data. Let's say we have 2 standard deviations. We first get this, then we get a bit more, then we get a bit more iteratively. If you guys remember, that is what we did also with our line fitting, right? Yeah, okay. In this case, MATLAB provides an estimate of your basically outlier ratio because it's a heuristic method, and it uses a type of method similar to RANSAC, okay, that you guys used, I think in lecture 3, was it? Yeah, to perform plane detection and plane fitting. Yeah, so it's using similar methodologies to that, okay? These are two strategies. A first strategy, do you guys remember what that was? To use median and median absolute deviation about the median, or the normalized one in this case. And why normalize? Normalize, it asymptotically goes to normality. So there is this, I don't know if I have it here. No, because I put it in a function. But if you take a look at the function of the MADN in your second lecture, you're going to be seeing that that particular function has a, coefficient 0.67 something. That coefficient is there. Why? So that it could provide you, okay, with asymptotic normality. That means that as the observations goes to infinity, that basically yields to normality as well, okay? Another way, which I like quite a bit, is to use the mode. And this actually turns out to give even better estimates of this center here. Why? Because this way, even if you have most of the observations here, as long as the majority of them lie in a particular place, okay, which is really the mode, you can still weed out even more than half of the observations, okay? Given that the initial set of parameters that you've estimated and you've gotten the residuals is close to your final, okay? If it's very far, then you're not going to get, let's say, a majority of the observations in one place, okay? So all of these starts becoming determinant of that, and that's why different methods are going to be performing differently in this situation. And sometimes you might need RANSAC-based methods, sometimes you might need AI-based methods to get a good initial estimates of your parameters before you can start performing these types of trimming and z-score basically outlier removal strategies. So these are the 4 strategies that we talked about. How can we improve it or perform it in our ICP? So I've given these basically functions there that you can utilize together with the functions that we've basically been creating throughout the course. What are the results? If you use the distance threshold at 0.1, which all of you already know what this is because you finished assignment 3, right? If we just keep this at this, using that basically set of data that I believe you guys did in your reading break activities, right? So this is the same, do you remember that historical site, whatever it is? This is basically one foundation of that. Now, if you do no outlier, this is what it provides. Essentially, it completely shifts it away. I think once we had an initial good estimation and we did 5 centimeters, it was close. But now that we're doing 10 centimeters, meaning we're doing it extra, it's shifting. It's actually not converging, it's diverging. How can we prevent that? This is basically what we're going to be doing, which is utilizing these outlier detection methods in order to be able to minimize the possibility of creating something like this and having less dependency on our distance threshold. I'm going to show that this can only be useful so much because once we're doing it in 20 centimeters, it still requires other strategies. And that's why we have to do it in different ways. Okay? So if you're using strategy number 1 with alpha 0.6, we're going to get this. 0.9, we're going to get this. So you're going to get a bit more here because it's trimming a bit less. Why? Because it's expecting more or less outliers in the 90%. Alpha 90% meaning that only 10% are outliers. Alpha 60% is meaning that it's 40% outliers, right? That's what that means. That's why if you take a look at it here, you're going to be getting a bit more points compared to this, which makes sense. If you're using strategy number 2, you're actually going to get even a better, you see, arrangement here. If you take a look at it here, this is still a bit slanted. This one gives it a bit of better one. Strategy number 3, and then strategy number 4 as well here as well. all of these are relatively good and definitely superior to the first one, which is not using any outlier detection strategy. However, you're still getting some points here, and we would like to even remove that to minimize as much as possible the impacts that these are going to be having on that. So what can we do? Which one would you choose now that you get these results? And with due consideration of your computation time, because some of these are a bit more computational heavy. Do you guys remember which one was more computational heavy? These number 1 and 2 are the ones that are going to take the most, okay? Strategy number 3 is actually the least, right? Because it only requires median and MADN, which only depends on the median, right? It's very fast to be able to do it, and you can parallelize it very well or vectorize it very well in MATLAB. Strategy number 4 requires you to have the mode. It's a bit more computationally intensive, okay? But for the majority of the times, based on my basically, experience, it actually gives very, very good balance between the amount of time that it's going to be taking versus the quality of the data that you're going to be receiving. The distance, we know that we can have some initial distance, and then we would have some strategy to be able to remove the outliers, but you're still going to have outliers if you're just doing it one time, right? So one other way is to do it many times, right? So iteratively, as much as finally it converges, let's say that 2 points or 2 sets of points between 2 iterations do not change at all, okay? That could be a convergent criteria. Because if you remember, what happened is that in the BIM simulation, we got every point to every surface. We calculated that. And then once we calculated it, we performed an ICP, okay? And if we do it one time, these are the results. What if we do it multiple times? Okay, so that's one strategy that we can employ, right? Which is exactly what we can do. So one way is to do it one time, and these are the results. Another way is to do it multiple times, which is similar to what we call a concentration step. What this means is that once you get this result, you again perform essentially the z-score, and then you get the results. And then you do it again, and then again, and then again, until no more outliers are removed. And that would give you the convergence. Sometimes you might say, okay, when the RMSE between 2 iterations is less than a hundredths of a millimeter, well, we're not going to get, in an engineering sense, significantly better results. Therefore, we would stop it there. So you can also justify it, especially if you're using metric scales. You could justify that, and more or less the order and magnitude of the error associated with your instrument. So for instance, if it's a laser scanner, it's within millimeters, right? So if the accuracy between the estimation of 2, let's say, iterations is less than 2 orders of magnitude compared to that, that definitely, in an engineering and applied sense, would be sufficient enough for us, right? Okay, so this is basically what we're going to be performing. So I called this first strategy, which is doing it one time, robust light, and if we do it in a concentration step, I call it robust strong. And this basically here, as you can see, removes all of these other ones, because every time it's basically iterating it and removing more and more and more outliers until no more outliers are removed, or until the RMSE, or the root mean squared error between 2 iterations, remains very negligible, the difference between that, right? And that negligible, if we have metric scale, I'm emphasizing on that in terms of the engineering, could be, let's say, 0.01 millimeter, okay? Or 10 to the power of minus 5 meters. That could be sufficient, okay? Make sense? Okay, if we use robust strong with strategy 3, this is what you're going to get, and with strategy 4. So pretty much the same one. Therefore, the one that is faster is normally going to be the best strategy that you're going to be utilizing, especially when you're getting the same results for different strategies, okay? In this example, they're providing very similar results as well. Make sense? Even if you're using some of these strategies, when you're increasing this threshold, it's also going to be even worse. So every time it starts becoming dependent upon the amount of threshold and then what strategy you're going to be employing. Therefore, we want to minimize that. We want to say, okay, if the user defines it 15 centimeters versus 20 centimeters versus 10 centimeters, what would be the result based on that, right? And then using that, we would be able to essentially decide on what would be the best strategy for that, okay? So, single stage outlier detection method is one way to go about it, okay? But we can also perform a Monte Carlo-based fitting method. Make sense? Right? Using a Monte Carlo-based fitting method, we would be able to see whether a particular surface has the same outliers or not, and then extract the information based on that, okay? And we can perform an iterative, basically, concentration step on the same surfaces. We can also combine some of these together as well. It's not necessary that much. However, if the initial set of observations is very far, you might combine a Monte Carlo-based method or an AI-based method to get the initial good estimates, and then using that, basically performing some concentration step to even adjusting and adapting to the final set of funneled inliers even more, okay? Yeah? So, what are the results there? Well, if you're using a disk, and this is for 20 centimeters, okay? This is going to be only ransack, no additional strategy on it, okay? This is going to be if we're using strategy free. Is there something better? Yeah, right? It's a bit better. You can see here, so it's the same threshold, initial threshold, but if we're combining some of these strategies, you're even going to be getting a bit of a better result. What about this one? Even better, right? So you're iteratively performing a robust concentration step, okay? And I want to emphasize, doesn't mean that the robust concentration is always the best, okay? In this example, however, it's superior. In many other examples that looks at linear and planar surfaces, it also provides very, very good results. So it's always good practice for you guys to have a few of these algorithms to pretty much compare with each other and see what would be the best result.